So lesson 2B, we're going to refer to the notes again. Part A, this is a repeat. It's the area integral connection. That was from lesson 1A. The fundamental theorem of calculus, part 2. The evaluation method was lesson 1B. We're going to just reiterate this. So the integral from A to B of f prime of x dx will be the antiderivative at B minus the antiderivative at A. And also, the integral from A to B, just written differently, if it's the antiderivative from A to B of just f of x, then we write the antiderivative as big F at B minus big F at A. Now we're going to look at part C, the fundamental theorem of calculus, part 2, applications. In the last video, we looked at position, displacement, and total distance traveled. Now we're going to be looking at accumulating quantities. A quantity might be the amount of stuff, it might be the amount of people, it might be the amount of sand, amount of water. So it just refers to the amount of anything. So we're going to say Q of t equals the amount of stuff, whatever that stuff might be, at time t. Q prime of t then, logically, is the rate at which the stuff quantity changes at time t. And if we follow the fundamental theorem of calculus part 2, the integral from A to B of Q prime of t dt would be, again, the antiderivative at B minus the antiderivative at A. Now we're going to look at the next page. On the next page, we're going to rewrite that Q of t is the amount of stuff at time t, and Q prime of t the rate at which the stuff quantity changes at time t. What we're going to add to this is that Q prime of t is going to incorporate two different rates. It's going to be some rate that's coming in minus some rate that's going out. Consider this scenario. Somebody is filling a pool with a hose. So there is a rate at which the water is going into the pool, but then also suppose that there is a leak in the pool, a small leak. In this scenario, you have a rate going in and you have a rate going out. And the rate at which the water quantity changes incorporates both that rate in and that rate out. We'll rewrite the fundamental theorem of calculus, the integral from t equals a to t equals b, Q prime of t dt is going to equal quantity at B minus the quantity at A. So we want to use some words to describe that, and you might think of that as the quantity displacement over AB. So for instance, if I say I have some pool and over a 3-hour period I lost 4 gallons of water, the displacement would be negative 4 gallons. Like we did in the last video, we're going to take and solve for Q of B algebraically, and you can see that to do that, all I have to do is add Q of A to both sides. So that gives me Q of A plus the integral from A to B of Q prime of t dt. Now in words, what is that? Well, obviously that is the amount of stuff, you might say the final amount of stuff at time B. And the final amount of stuff always depends on how much stuff I started with. So I look at how much I started with, and then I add to it the displacement. So suppose that somebody said, yeah, over a 5-hour period of time, I lost 50 gallons of water. How many gallons of water does my pool now contain? Well, think about that. You should respond with a question in return, which is, well, how much water did you start with? So the final amount of stuff includes the starting amount of stuff plus the displacement of the stuff. Let's take a look at some examples. Example 1. The rate at which people enter an amusement park on a given day is modeled by the function E defined as you see here. The rate at which people leave the same amusement park on the given day is modeled by the function L, also as you see here. What I'd like you to do before answering any of the questions, I just want you to put these two functions into your calculator as y1 and y2 respectively. Once you have them entered into your calculator in y1 and y2, I'd like you to turn your calculator off and put it away and follow all the examples until the end, at which point you will go back, use your calculator to compute the answers. To start off the problem, we're going to define the quantity of stuff, the thing that we're talking about, the thing that will grow and decrease, and that thing here is the attendance in the park, the number of people in the park. I see down here part C that they're going to tell me that instead of Q of t, we're going to define it as H of t. So again, I haven't started the problem, I just want to define what the quantity is. So H of t equals the number of people in the park at time t. We also want to define the rate in, rate out functions. So E of t is the rate at which people enter the park, so this will be our rate in, rate adding to the amount of people in the park. And then the L of t would be the rate out, the rate at which people exit the park, taking away from our quantity, H of t. Let's take a look at part A. How many people have entered the park by 5 o'clock? T equals 17. Round to the nearest whole number. I wish you were in class now, if you weren't, to see it the first time, because a lot of people will accidentally say E of 17 is the way to represent this answer, and this is not correct. What does E of 17 represent? Well, if E is the rate at which people enter the park, then E of 17 is the rate at which people are entering the park at the time t equals 17. So at 5 o'clock p.m., people are entering the park at a given rate. That is not what we want to find. The thing we want to find is how many people have entered the park by 5 o'clock. What we want is the integral from 9, that's the time when the park opens, till 5 o'clock, which is 17, of the rate at which they enter. Again, they're not asking how many people are in the park. They want to ask, in this problem, how many people actually came into the park. So suppose we gave a ticket to every person that came in. This would be the number of people who at least had a ticket. E of t is a rate, and dt is a time. So the number of people per hour times the time would give you the number of people, rate times time. When you integrate over a rate, you get an amount of stuff, a quantity. In part B, the price of admissions to the park is $15 until 5 o'clock, and then after 5 o'clock, the price of admission goes to $11. How many dollars are collected in admissions to the park on the given day? Well, it'll be $15 for each of the people that entered between times 9 and 17. And then we're going to add to that $11 for all the people who entered between the hours of 17 and 23. So the integral from 17 to 23 of E of t dt gives us the number of people, and then this entire expression gives us the amount of money that was collected. Part C. Let H of t be the number of people in the park, and we want to find H of 17. We want to find how many people are in the park at time 17. If you remember from the brief introduction, if I'm asking you how many people are in the park at time 17, you have to first ask how many people were in the park when the park opened, or how many people were there initially. So we have to consider how many people were in the park when it opened, H of 9. And then we want to add the number of people who came into the park from 9 to 17. But then we also want to take away the number of people who have left. and that would be the integral from 9 to 17 of our L of t function. It's like saying the door's locked. There was a major lockdown at time 17. How many people are in the park at time of lockdown? Well, a bunch of people left, so they're not locked in, and so we have to incorporate how many came in, and then subtract how many people have already left at time 17. All the while considering how many people there were when it first opened. Now, h of 9 in the problem, the number of people in the park when it opened, is actually 0. So this guy here is 0. It's not needed, but I really like you to write it so that you show that you're considering that it could be something other than 0. And then the other thing we can do is combine these two integrals as one integral and say the integral from 9 to 17 of e of t minus L of t, which would be the rate of change in the quantity of number of people in the park. Lastly, let's take a look at part D. It says write a function involving an integral expression for h of t, the number of people in the park at time t. So not h of 17, but h of t. So we'll say h of t equals, again, we'll consider how many people were there when it started, plus the integral from 9, and instead of saying 17, we're going to use the variable t. Now here is a very important part. We don't want to use t in the integrand. If I have my variable of interest as one of the bounds, here's my variable of interest. If I have the variable of interest as one of the bounds, I do not want to put the variable in the integrand. I need to use another variable to temporarily hold its place. And I will explain this in a second, but first let's just write it. So normally here we would say e of t minus L of t, but I'm going to use what's called a dummy variable. In this case I'll use u. E of u minus L of u. You can use any dummy variable. You could use x, you can use s, you could use a smiley face. But it's a temporary variable that holds the place of t. It's called a dummy, not very nice, a dummy variable. Putting it together, h of t equals h of 9, which is 0, plus the integral from 9 to t e of u minus L of u du. That is the answer to part D. I would like to take a moment to explain why we need a dummy variable. So we'll come up above here and take a look at it. Consider the function f of x equals x to the power of x. And when you were first introduced to function notation, if someone were to ask what is f of 3, you knew you had to plug in 3 to all places where the variable was x. So this would be 3 to the power of 3, which is 27. Now consider this function. F of t equals the integral from 9 to t of e of t minus L of t. So in this case, I don't have a dummy variable. Then if I were to ask to find f of 17, like we did in part C, then I would have to plug 17 for all t's. So that would be from 9 to 17, but then I would also have to plug it in here. E of 17 minus L of 17 dt. The problem is this gives me a number. It's not a function for which we want to integrate over. It's a number that we're integrating over. So this would be bad. But if I let the function f of t equals the integral from 9 to t of e of u minus L of u du, then when asked to find f of 17, I know that I need to plug only into the bound 9 to t, or 9 to 17, because I plugged the 17 in for the t, and I would know not to plug it into here because it is not of t, it is some other variable. But now that I have this bound at 17, I can write e of t minus L of t back to the original variable definition. And that hopefully explains why in our function of t, when t is in the bound, I need a dummy variable in the integrand. Now it is time to evaluate each of these functions. So you'll want to pull your calculator back out so that we can evaluate these. Remember, e was y1 in our calculator. So take a moment and find the answer rounding to the nearest whole number. The answer should be 6,004 people. You may have needed to say diamond enter an effort to get that answer. And I'd like to come over just to review the syntax. This would be the integral of, we would say y1 of x with respect to x, and then we would take that comma 9 to comma 17, and that would yield the answer here. Again, diamond enter to get the approximate, which we rounded to the nearest person. Let us continue now by finding the amount of money, again rounded to the nearest dollar, and the answer to this will be $104,068. You can do that in one step in the calculator, pressing enter only once. The syntax is shown here. Now finally, let's evaluate the answer to part C. The answer is 3,725 people. Notice that is less than the 6,000 people that were at time 17. The 6,004 were the amount of people who actually came in, and then we had to take away the people who actually left the park. That's why this answer is less than the answer in part A. You might notice that in the syntax I used the y1 of x minus the y2 of x in one single integral expression. That is the end of example number 1.